When you architect cloud-native platforms, planning for physical hardware failure is a foundational requirement, not an afterthought. To design a system that survives hardware volatility, we first have to separate scalability from high availability. Scalability is simply an application's mechanical ability to handle greater transaction volumes by adapting its resource allocation. This animation illustrates the first scaling vector, vertical scalability. This involves scaling up by increasing the physical or virtual resources allocated to a single operating system instance. You can scale a workload from a fractional T2.nano instance all the way to a U12TB1.metal instance, which delivers 448 vCPUs and 12.3 terabytes of RAM. But the expansion stops there. Once your instance hits the maximum physical capacity of the underlying host hypervisor, you cannot provision a larger machine. Because vertical scaling is bound by immutable physical hardware constraints, achieving unbounded growth is impossible without structurally refactoring your codebase into a distributed model. This diagram demonstrates the structural alternative, horizontal scaling, or elasticity. Instead of upgrading a single machine, you adjust the number of independent, stateless operating system instances running in parallel across your fleet. By treating compute as a distributed, parallel resource, horizontal scaling in Amazon EC2 removes those hardware boundaries entirely. While horizontal scaling solves capacity limits, it does not guarantee uptime. For that, we configure high availability, which dictates that your application must run across at least 2 discrete availability zones. An availability zone provides geographic disaster isolation. Each zone consists of physical data centers equipped with redundant power grids, independent networking, and low-latency fiber connectivity. This multi-zone distribution can take different operational forms, from an active-active horizontal EC2 fleet continuously processing requests to a passive active standby database failover. True cloud scalability requires decoupling the application from a single physical host and distributing parallel instances across these fault-isolated locations. Distributing traffic across a horizontal fleet requires a centralized load balancer to act as the traffic gateway. This introduces a specific security challenge: how to prevent clients from bypassing that gateway and hitting your backend instances directly. This schematic secures the entry point using chained security groups. First, the load balancer security group allows incoming HTTP traffic from the public internet. Next, the backend EC2 instance allows zero public access, explicitly referencing the load balancer's ID as its only source. AWS enforces this with a stateful firewall engine evaluating packet origin metadata. If a packet bypasses the load balancer, the EC2 instance identifies the incorrect source and drops the connection. Conversely, packets routed through the load balancer possess the correct association and pass through. By utilizing stateful origin metadata validation, we achieve backend isolation, ensuring all incoming traffic adheres to the centralized policies defined at the load balancer. With the network isolated, we have to dictate how traffic physically routes to the instances. The earliest implementation in AWS was the legacy Classic Load Balancer, a version 1 router operating at both the transport and application layers. A standard Classic Load Balancer architecture relies entirely on dynamic DNS hostnames because its underlying IP addresses rotate continuously during scaling events. To prevent routing to dead nodes, the CLB evaluates backend health utilizing TCP socket checks alongside Layer 7 HTTP response validation.
Today, the modern standard is the version 2 application load balancer, which discards transport layer routing to operate strictly at Layer 7. The ALB intercepts incoming traffic and evaluates HTTP headers and URL paths, routing requests based on application logic rather than simple port mapping. Instead of mapping to individual instances, the ALB routes traffic to target groups, a flexible backend abstraction isolating resource pools. Target groups support diverse configurations, routing to auto-scaling EC2 fleets, ECS containers, or private IPs. When routing to serverless endpoints, the ALB automatically translates incoming HTTP request metadata into a standard JSON payload before invoking a Lambda function. Operating entirely at Layer 7 gives the ALB native support for modern protocols like HTTP2 and WebSockets, alongside the ability to manage custom health checks based on specific HTTP status codes for every independent microservice. Application load balancers transform basic load distribution into context-aware traffic routing, allowing you to run decoupled microservice architectures safely behind a single secure entry point. Deep packet HTTP inspection requires computing power. For systems requiring millions of requests per second, the application load balancer's evaluation overhead is an unacceptable bottleneck. To eliminate that latency, you deploy the network load balancer, a specialized solution built for extreme throughput architectural demands. The network load balancer operates exclusively at layer 4. It does not terminate client connections, and it never inspects application layer HTTP headers. Instead, it processes raw TCP, UDP, and TLS traffic directly at the transport layer, acting as a highly efficient pass-through forwarding straight to target groups. Bypassing the transport layer grants AWS the ability to allocate exactly one static elastic IP address per availability zone. The traffic flows with zero connection termination directly into backend target groups, a mandatory requirement for enterprise firewalls utilizing strict IP whitelisting. Selecting your routing topology demands an exact trade-off calculation between the deep packet inspection of an ALB and the raw, low-latency transport speed of an NLB. Regardless of which load balancer you choose, your infrastructure will be volatile. Removing instances from a target group for patching or scale-in operations creates a high risk of active transaction failure. If an instance vanishes while processing a client request, the connection drops. To prevent this, load balancers implement connection draining, or deregistration delay. When an instance enters draining state, the load balancer halts routing new connections, but keeps existing sockets open to finish in-flight requests. You configure this timeout from 1 to 3600 seconds. If it expires, remaining sockets are forcibly severed and the instance removed. These state preservation mechanics ensure your fleet remains elastic without dropping in-flight packets, providing a stable user experience even as underlying compute nodes are recycled. Reviewing the complete logical architecture, we bypassed physical vertical limits via horizontal elasticity, lock down the internal network using stateful security group references, and dictate exact traffic flows via OSI layer-specific load balancers. But load balancers only distribute traffic and protect connection state. They do not possess the ability to dynamically launch or terminate the EC2 compute fleet themselves. To automate compute generation, we have to integrate auto-scaling groups, build deterministic launch templates, and write dynamic scaling policies. That automated elasticity is exactly what we will deconstruct in the next video.